Oh boy, upside down again. One of these days, I'll remember what's supposed to be up. Alrighty. So, hopefully we'll trickle in a little bit more as we go. Before we hop in too much, were there any quick questions that folks had about the exam? I'm not sure what you mean. I mean, if you have any questions, we'll go over right now. You mean, like, do you want me to do something like what was on the exam now? Yeah, absolutely. Like number 8. Sure. It's going to be one that's useful to have an actual good point. Sure, we'll do that one. So, yeah, we can do something like number 4. Okay, so this one here, the hint on the exam says, what does a line horizontal say about the slope? So what does it say about the slope? Right, so horizontal, as you say, means that the slope equals 0. And so how do we get the slope of a tangent line? Right? So the slope of the tangent line is the derivative. So if we want to find a horizontal tangent line, we need to figure out where the derivative is 0. So, how are we going to find y prime for this equation? What method will we be using? Implicit, right? So there's no way to take this equation and solve it for y. So we're going to do implicit differentiation. That's spelled mostly correctly. So, if we remember how to do that, remember that's taking the derivative with respect to x, and y is secretly a function of x, right? So this first term becomes 6x. This second term, that y squared, y is a function of x, so we have to use the generalized chain rule. This second one here, we're multiplying two things. One of them secretly has an x in it, so we got to use the product rule. So that's the term where we take the derivative of the first piece, and that's the term where we take the derivative of the second piece. And 24 is just a constant. Right, so do we have any questions about where I got this guy from? So from here, there's two ways we could go about it. In general, if we want to find y prime, we would solve for it. And then we'd set equal to 0. Right? But specifically because we have that second thing to do, we could reverse that order and set y prime equal to 0 and solve. Right? So we'll get the same basic thing out of it, mainly because if we're trying to set a fraction equal to 0, we set the numerator equal to 0, and that's basically what we'll get for both of these steps, regardless of what order we do it in. But I like this second one. It seems a little bit easier to me because from there, we just have 6x. The term that I circled there becomes 0. Because y prime is equal to 0. This term here also equals 0 because y prime is equal to 0. And we just have this guy. Any questions about any of the steps here? I set y prime equal to 0 in this guy here. Right, so if y prime is equal to 0, this guy that I circled, 8y prime, is 8y times 0, and that's just 0. Right? And this guy over here with the squiggly thing above his head, if y prime is 0, 3x times y prime is 3x times 0, and that's just 0. So the only thing we have left over is the 6x in a box, this 3y that's been underlined, and a 0 on the other side. Does that make more sense? Cool. So if we simplify that piece, we get this guy here. And this is where the second half of the hint comes in, which says, also recall that the point x naught y naught you find has to satisfy the folium equation too. Now, we don't have a folium here, we just have a regular equation, but to get a point on the original curve that has a horizontal tangent line, we've focused all of our work on figuring out where the tangent line might be horizontal. So we need to figure out where on here it will be horizontal. Right? We need to combine both the original curve and the horizontal tangent lineness. So we're going to take this equation that I circled in green there and plug this equation circled in orange here. So at least the way I solved it, it's easier to plug in for x. That makes sense to folks? Do we see where that comes from? I don't want to scroll up till I make sure we're on the same page, because then I'll just have to scroll back down again. So if we take this equation here, we subtract 3y from both sides and we divide by 6. Alrighty. Go on and give us some more room to work with this guy. Alright, so now that we've combined the equation of the curve itself with the places where the derivative will be 0, then we just need to solve that. So it's nice enough that we just have a whole bunch of y squareds here. So that's going to be pretty easy to solve. We're going to want to put everything over 4. Or alternatively multiply through by 4, but there we go. Alrighty. Now there's probably some things I can pull out. Like I know there's at least a 16 that I can pull out of the top. But that doesn't really simplify it much for us, so. And since we want points, right, that means XY pairs. How can we get the X part of these XY pairs? If we have some Y's, where do we think the X is going to come from? Yeah, exactly. Right? So we have that equation. We know that if the tangent line is going to be horizontal, then x is always going to be equal to negative 1/2 y. So if we want the tangent line to be horizontal, and we have some y's, then x is just going to be negative 1/2 times those y's. You could also, technically, if you like, plug it into your original equation, but I don't really want to read that algebra, personally. It's always best if you have two options of what to plug in for and solve, pick the simpler one. So any questions about what we got here? Or anything we've done on this problem? Alrighty. So, we had a request for like number 4. And I'm going to go through parts of that pretty quickly because we've done one in more detail like this before. But we'll talk a little bit about it. So let's have right, and so this problem says to calculate several derivatives and look for a pattern, and then try to find an expression for the nth derivative. Right, so we're going to get our first derivative. It's going to be the product rule and the generalized exponential rule. So if we take the derivative of the first, we get negative sine of t. And then if we take the derivative of the second, that 2 comes down. And the e to the 2t stays the same. Right? That's our generalized exponential rule, is that we just keep the exponential but multiply it by the derivative of the power. Yeah, we can probably do something like that. Alright, so the second one, second derivative, now we have two pieces that we're going to need to use that product chain rule combo on. So for the first term, we take the derivative of the first times the second, plus the second times the derivative of the first. And then for the second term, we do the derivative of the first times the second, plus the first times the derivative of the second. I need a better eraser than that. There we go. Whew. So we can combine this so that we don't have quite as many terms flying around. Let's see. Checking through to make sure I did my derivatives right there. Y'all are welcome to as well. And one of the things when you do something that involves the product rule and a trig function, you're probably going to need at least 4 to try to figure out a pattern. So again, working off of this guy, this is going to be the product rule. So the derivative of the first times the second plus the first times the derivative of the second, and then this second one the derivative of the first times the second plus the first times the derivative of the second. And again, we want to combine these because we've got similar terms, and there's no need to do 4 product rules when we can do 2. Not being careful about my negatives. Well, that's a nasty pattern. Alrighty, let's do one more. See if something comes of it. So the derivative of the first times the second plus the derivative of the second times the first then, oops, we have the derivative of the first times the second and the derivative of the second times the first. Again, combining those like terms. Okay, so let's see what we can figure out for a pattern. So we're definitely switching back and forth, sort of crazy pants between negatives and positives. Though sine seem to always be negative, cosine is the thing that is going back and forth. Give us the original a little bit. Yell out if you see any patterns as we're going through. This one is a little bit more different from the sine one that I was intending it to be. But one thing you can do, right, if you get stuck on this one, as I'll be honest, I kind of am with what we got here, is describe what patterns you do see, right? Even if you can't come up with a formula, the point of this problem is looking for patterns. Right, so one thing I can notice is that in all of these, the sine term, which there always is one, is always negative, and it's going up. So from here to here, right, so -1 to -4. Right, and then it goes to -11, and then it goes to -24. So, whew, that's a weird pattern. Right, I definitely can't think of much of a formula that gives me 1, 4, 11, 24. But I can make the observation, oh no, we're going up by odd numbers, and we seem to always skip an odd number. Right, so that's kind of a pattern that we could observe. Here, even if we can't find a formula for that. I'll be honest with this one, cosine, I don't really see a formula there. It's behaving very oddly. So yeah, the different starting point got me further away than I expected. But this is how you would set it up, right? So this is going to get you some part of it. I can work out a different one when I have more time to look at it and maybe explain more. So for this one, I'm probably going to be fairly generous with the partial credit, considering that I'm pretty sure the one on the exam works out better, because I've actually worked that one out, and I don't remember it being this crazy. But go through a couple derivatives, try and look for patterns, describe what patterns you see, even if you can't find a formula. Talk about what seems to be consistent, right? Like the fact that, I don't know, maybe it's cosines in that one that are always either positive or negative, and maybe you can't find a formula for it, but you can describe it in words like we did here, right? So it goes up by an odd number, skipping one each time. Right, we skipped 1, we skipped 5, we skipped, well, I guess we skipped 2 here, didn't we? So yeah, do your best to describe what patterns you see, look for patterns, and I will be very generous with partial credit for this one, especially if it turns out to be as obnoxious with the sine as the cosine. Right, does that sort of help with that one? I didn't have time to prepare one that was as like the one on the exam as possible. Again, if there are any more questions about that one, feel free to throw them in there, but... So for... Oops. Number 1, what I might do there instead of working out an entire problem is sort of explain what we're dealing with. Right, what sort of things do we have that talks about initial velocity and catapults throwing things upwards, and things like that? Where have we seen that sort of thing before? Yeah, the rates of change section, right? So I think that's 3.4. And in that section, we have that the position function for the movement of an object that's being affected by gravity, right? So it's under the section motion under the influence of gravity, is S naught plus V naught T minus 1/2 G T squared. Right, and of course that means that velocity, which is the derivative of this guy, is going to be V naught minus GT. right? And so what is S naught? Right, so that's our initial position. So as we're looking at a problem like this, if we're told any information about where the projectile was shot from, where it was thrown from, where we're standing, that's the thing. Yeah, we're not doing this particular problem. I'm trying to do it a little bit more in general. But yes, for this one it is 8 meters. And the T here, what does the T stand for? Right, time. And we already said this is position, and this is velocity. Right? So like I said, I don't want to work through a full problem because I'd like to get a little bit done on this section. Because we do have some responsibility to get through some stuff, despite everything going on. But as you're looking for a word problem like this, right, your sort of initial position is where you're starting from, where it's being thrown from, where it's being shot from. V naught is your initial velocity, as the problem says. So that one's probably going to stay unknown for this, because that's what the question is asking for. Then any sort of times that are given are going to be plugged in for a T somewhere. Right? And then if you're told about what position it's in at a given moment, then you're going to plug that T into S. And if you're told what velocity it is at a given moment, then you're going to plug it into V. Right? So hopefully that'll be a good setup for number 1 there. Do we have any other quick questions that we could go over? Okay. So to get this actual section underway a little bit, right, so the main thing of this section that we sort of start from is the mean value theorem, which I will almost never write out that way again. I will usually write out NVT. Right? And so what that says, if f is continuous, Okay, so if f is continuous on a closed interval and differentiable on the open interval inside that, then there's going to be at least one point inside that interval where the derivative at that point is equal to this formula here. Right? Which actually looks a lot like delta y over delta x if we were to put a fine point on it. Right? So one thing to notice is that if f of a equals f of b, then the guy on the right is just 0, right? Because f of b minus f of a is always 0. And that is what last section called Rolle's theorem, right? So that's why we didn't do too much with Rolle's theorem, is Rolle's theorem is really just a specific example of the mean value theorem. And another consequence that we have here is that if f prime of x is equal to 0, so if the whole function is equal to 0, not at a particular point, but if the whole function is, then the whole function itself is equal to some constant, right? That k just stands in for a constant number, right? So maybe it's 1 or 2 or negative 50, but it's some constant number. It doesn't change depending on x. Right? And the last way we use this is to check for monotonicity. Right? So I think I spelled it correctly there. We're going to hope. Right? Remember, that is talking about where functions are increasing, like here, or decreasing like they are here. And of course, here's another increasing. Right? So the descriptions of increasing and decreasing are whether they're going up and down as we go from the left to the right. So turns out that the derivative can help us figure that out. So increasing is when the derivative is positive. Decreasing is when the derivative is negative. And this also helps us combine with last section to figure out when crit points are maximums or minimums. So if we have a crit point here, and f of x was positive before that crit point, then at the crit point it's either going to be 0 or non-existent, so it's either of those here, and then it goes to negative. Then this means we have a local max. If it's negative to the left of the crit point and positive to the right, then we have a local min. If it's not either of those cases, then it's neither. So if it starts off negative and ends up negative, or if it starts off positive and ends up positive, then that means that crit point is neither a maximum nor a minimum. Right? We talked about last section that every maximum and minimum is a crit point, but not every crit point is a maximum or a minimum. So what we had to do last section is we found all of our crit points and we plugged them in, and we figured out which ones were the biggest and the smallest. Here, we can just figure out whether they're one of these local maxes or mins. Right, so it's also different from last section. In the last section, we were trying to find the absolute max and min. So, let's start off with, well, we're going to start off with a problem that I'm mostly just going to do because it's really hard to have you describe to me how to draw a picture. But it's one type of problem that can come up from this stuff. So if we know some stuff about the derivative, we don't know what the derivative is, but we have some ideas about how it goes. Right? Then that can let us draw a picture of the function itself. It's not going to be a very accurate picture, and I'm not even going to draw the y-axis because we don't know how tall or whatever it comes in. But we do know that from -2 to the left, right, for everything less than -2, f prime of x is greater than 0. It's positive, so we know the function needs to be increasing. So we'll go up to, I don't know, there. And we're increasing the whole way. Right? Now, between -2 and 5, I sound like a little bit. Between -2 and 5, the derivative is less than 0. So we don't really know what it looks like exactly. So again, there was some artistic license taken here. We don't know exactly what it looks like. We don't know how high it gets. Right? That might also describe... no, that's not a good color. I know that's not a good color. Here we go. No, maybe this will be a decent color. Right? It might also describe this function... Right, because that is also a function that is increasing, decreasing, and constant on the right intervals. Right, so this by itself, what we've got here in this section, can't tell us what exactly the function looks like. Right, but it can give us a basic idea, right? These guys sort of have the same shape, at least the same very, very basic shape. And that they go up, and then they go down, and then they go flat. So maybe if we had a couple of options, we'd be able to say, well, this one definitely isn't this function. Right? But we can make sort of this, this guess at what the function is. based on just the derivative, right? But it's always just going to be a guess, at least with the tools we have so far. Any questions about this guy? Alrighty. So if we have a function f of x, which is this polynomial here, let me make that a little bit easier to see. How can we figure out where this function is increasing and decreasing? What did we learn about in this section about when a function is increasing and decreasing? What does it maybe say earlier on the screen that we have right here in front of us about when something might be increasing or decreasing? Yeah, right? So the rule we have for increasing and decreasing in this section is that it's increasing if the derivative is positive, and it's decreasing if the derivative is negative. So if we want to be able to find where this function is increasing and decreasing, then we need to find the derivative. Right? Because our rule is all about what happens to the derivative. So, what's the derivative of this function? power rule. On all of those terms, get this guy. So when is the derivative going to be positive and negative? How can we figure that out? Anybody remember this from pre-calculus? So oddly enough, the first thing you want to do when you're figuring out where something is positive or negative, at least for a polynomial, the first thing you want to do is figure out where it's equal to 0. So where is this quadratic going to be equal to 0? Four and 2, right? And we can get that by factoring this to x minus 4 and x minus 2, because negative 4 and negative 2 multiply together to get positive 8, and they add together to get negative 6. So that means that this is at 2 and at 4. And the reason why we find these zeros first is that for this entire block, it's either going to be positive or negative, right? For this entire block, it's either going to be positive or negative. And for this entire block, it's either going to be positive or negative. So to figure out where it's positive and negative, we just have to figure out what it's going to be at one point in all of those. So what's our favorite number that's less than 2? There are no right or wrong answers. I just need a number less than 2. preferably one that's easy to plug in. 1. Sounds good to me. Alright, so if we plug that in, we get 1 minus 6 plus 8, which is 3. So we get a positive number there. What's our favorite number that's in between 2 and 4? That's easy to plug in. 3. Sounds good to me. So we get 9 minus 18 plus 8. I think that's negative 1. So we get negative here. All right, and what's our favorite number bigger than 4? Five. Sounds good. So we get positive again. All right, so that tells me it's increasing on negative infinity to 2 and 4 to positive infinity. Right, the other way to write that is x less than 2 and x greater than 4. Either one of those is fine. And it's decreasing between 2 and 4. Where you have those two ways of writing it out. Any questions about what we got there? So, we definitely don't have time to do another problem, and we didn't get much practice here, but thankfully the next section of this book is kind of, let's do all this again, but for the second derivative, so it'll tell us slightly different things. So what I'd like to do is sort of combine the next couple of problems with next section. So I'm going to go ahead and set up the reading summary for next section. And our next couple of practice problems will have us doing stuff from this section and next section on the same function. Right? So we'll just sort of combine our practice problems and still talk about classifying crit points and using the first derivative test and the second derivative test, which is what we get at next time. And finding increasing, decreasing, as well as concave up and concave down. If we have any other quick questions for the next couple minutes, we can go over that. Otherwise, I guess I'll see you on Wednesday. See everybody Wednesday then.